Okay, good evening. Welcome in the first week after midterm 1, week 5. And you may use the chat box just to confirm that you can hear me. Okay, yes, thank you. You may type good evening. It's okay. Thank you for confirming. Let me see. Okay, now I see better the chat box. Okay, that means welcome back after midterm 1. We went through the midterm 1 and congratulations, because we really have good numbers. I don't really know the average. Hang on, let me. Okay. Oh, I don't know how. You can see me, right? Always the settings are weird. Yes, thank you. Okay, that means I don't, because the average is not really important and it's not the indication of the output. I mean, it's not a good number, I would say, statistically, because what's happened, we do have lots of students with 100% points on the test, above 90, above 80, and even below 80 or above 70, it's still a good score. And that's me. This is the good, fantastic indication that you definitely work hard, put lots of time, and that's the output. We also have a little bit of numbers of students like below the passing rate. That means if I take the average, of course, it's not good, but this doesn't mean that you were not prepared. That means I really believe everybody did the good job. I still had a few students which I believe they are a little bit lost, because the day or the due date, Monday, June 11, they emailed me, oh, can you send me a password because I'm trying to take the test and I can't. Of course, you can't send email like that, especially like few minutes before closing date. I mean, closing time. Yeah, I'm saying like almost a midnight. Okay? That means you really have to pay attention what your instructor is saying. Especially we start this week with the week without any instruction, and that was the introduction to the course. I was trying to show you all of the folders, all of the files on Canvas, and I was trying to convince you that you have to know how to navigate, how to go through like on the daily basis. That means in order to be successful, you have to be really aware what's going on, and especially listen what is your instructor like telling you. Right? It's really helpful. Okay, that's a little bit of tips. I also have, but probably it's not. I think I have 1 or 2 students taking a test at Examity. I have the access to all of the recordings. That means occasionally I watch some of them. Of course, I can't watch all of the 90 minutes of every single student, but I'm also getting reports from Examity, and I've got 2 red flags. Okay, this means that you did something which you shouldn't do. I will double check. I still didn't get the recording because for some reason was not available. I will check the recording and I will contact the students, and probably the exam score must be different. I mean, I have to change, respectively, whatever happened during the test. That means please remember, in order to focus, to have undivided attention for your test, you have to pick the quietest room that is available for you, the quietest room, the tidy room. Like don't pick the messy room, because you can't really think in the messy room. It's like a classroom. It's just the desk and the chair. The room that is not accessible to everyone for this 90 minutes. Okay, and yes, and then you can take the test, and don't take to the room your phone and electronics, books, because that's also not good. Try to have empty desk and that's it. Then you're not giving a reason to your proctor like to stop and to interrupt, and like she or he will ask you, please show me the desk, please show me the surroundings. No, just try not to give her or him a reason. And also, they really watching you. I don't know how big you see me, but that's what they see. They see They see your white screen. I mean, they see your test and they see you. That means they is really watching you. Do not make any like weird movements, or do not cover your eyes. Okay, that's not good. Okay, we know what this means. Okay, that means don't do. I don't know why. I watch few videos and yeah, the students are doing, I don't know, you looking somewhere. Even if you're not looking, don't give this weird impression. Yeah, this suspicious eye movement, or of course talking to somebody in the room. That's not really good. Okay, but as I said, I'm just talking to maybe 2% of students. Most of you, I would even say all of you, did excellent job, and I'm really, really happy. And I'm actually extremely happy with your like that you devote your time. You're really working, and I like the discussions. Yeah, I see, of course, frequently the same names, but it's fine. I love the discussion. I love that you're answering the question between each other. I really like it. Okay, let's start. Oh, hang on, we have a question. Can we go to the bathroom? I don't think we can go. Yeah, I should also say, go to the bathroom before. Do not maybe drink, I don't know, before, or I don't even know if you can have a water, but I don't think you can leave the classroom. Yeah, maybe emergency, but I don't know how this, yeah, emergency, you can bring the laptop. Yeah, maybe you can take your laptop with you, kind of. Yeah, I don't know, I just see. But I will say, I don't know. I can tell you, I don't know if you can actually have a bathroom break. I can double check. This is a good question. I didn't even think about this. But I will assume that no. Yes, we can't really eat. Yes, different. Yeah. Good, yes, good comments. That means, yeah, just be, yeah, try to be responsible. But as I said, I'm so happy. I just have a few students that, but we always have, we know the normal distribution, right? That's kind of like always the outcome of everything of the society is like that. That's mean we always have this a little bit of percentage of people that are like kind of lost in the normal situation. It's perfectly normal, and I really don't want to like leave these students. I want, because I really care, and I like everybody to succeed. Right? That's mean just a few tips. Okay, that's me now. Let's start. Yesterday you had a session with Dr. Bank, and I believe he covered what we have this week. He finished chapter 8 with the L'Hopital rule, right? In the indeterminate forms of the limit. And what was other one? In improper integrals. Okay, that's mean the integrals with we have two types. Integrals with one of the limit being infinity, or other type is if we have discontinuity on the given interval. Okay, that's mean that's theoretically old stuff. That's mean now what we will start. We will start chapter 11, which chapter 11 talks about the infinite sequences and series. But the first section is just about the sequences. Okay, that's mean I will try to introduce this. And let's see, that means this one is still, we will use calculus. I mean calculus in the, generally speaking, like derivatives, integrals, but it's a little bit different part of Calc 2. Okay? And maybe that's the reason that calculus 2 has this not good reputation. Always everybody is saying that it's a really difficult class, maybe because of 11. I mean chapter 11. But I don't know. Again, if you really put the time and effort, you will ace it. Okay, sequences. That's mean what it is. I do have becomes harder. Okay, that's mean, do you think becomes harder and harder? Of course, we covering more and more stuff, but I don't know if I agree that it's different, right? And it's we learning higher and higher level of math, but I don't know if it's harder or harder. It's just, yes, like maybe the semester is long, maybe it's summer, maybe it's different components of everything, but Okay, I'm not going to say that it's harder and harder. I will always say that it's nice and easy if you have a good approach. Practice questions can be, of course, we always have lots of practice questions in the textbook, or even in doing the homework assignment. Yes, we do have lots of practice problems, but the suggested homework assignments are the best, I would say. Okay, let's see. Oh, I have to. That means what is sequence? Okay, that means sequence. It's just the same definition, like not even mathematically, but mathematically this means that this sequence is simply a list of numbers, okay, but written in the like defined order. Okay, we really have to have a appropriate order. That means we have a list of numbers, and we have a sub 1, comma, a sub 2, comma, a sub 3, 4, and so on, a sub n. Now let's see. Actually, I can show you the whole slide. Okay, that means, of course, a sub 1 we will call first term. A sub 2 we will call the second one. A sub n we will call the nth term. Okay, and then eventually, if I would like to, because I don't know how many of these terms I have, and most likely we will have infinitely many of them, okay, we will know the pattern. That means as soon as we know the pattern of the terms, we can create next one and next one and next one. That means we can have infinitely many of these terms. Okay? That means we will call the nth term, okay? And then the next one we will call successor. That means the term a sub n plus 1. And the next one will be the n sub n plus 2, and n plus 3, n plus 4, and so on. Okay? That means I can even write for you n plus 1, n plus 2, and so on. Also, we may define a term which is before a sub n. That means this one will be n minus 1, or even n minus 2. That's n actually. Okay? And so on. That means that's important. That means what is actually important to remember now, n is simply a natural numbers, or we have also a name counting numbers. Okay, that means this is a counting numbers, which means it's the positive integers, 1, 2, 3, and so on. That we can see. It's kind of like discrete mathematics. Is we only talking about, like, we will have if we want to see this as a function, which we have an input and an output. That means for output 1, I have a sub 1. For output 2, I have a sub 2. That means I have, if I will see my x, I mean the number line, I will only have numbers, the positive integers, 1, 2, 3, 4, and so on. Nothing between. Okay, that means that's also important. And natural numbers are the counting numbers. That means when I count something, when I count my terms, or let's say I will count my students in the classroom, I will count 1, 2, 3, 4. I will not start 0, 1, 2, 4, and so on. 1, 2, 3, 4. But sometimes we actually using a number 0. Okay, I can't really say this is the natural number. It's not. But sometimes we like to have the term a sub 0. But you will probably see. Okay, a sub 0. It's not, normally it's like 1, 2, 3, 4 is counting numbers, but sometimes we have a sub 0 too. Okay, that we know how to define the terms. The first one, second one, and so on. And make sure that you understand this. The n plus 1, n plus 2, n minus 1, n minus 2, and so on. Okay, we good with the notation. No question? No question. Okay, and now, the kind of what I just said, we can define a sequence, okay? That means, of course, every positive integer corresponds to the output a sub n. That means we can call a sequence, we can define a sequence as a function, okay, whose domain is a set of the positive integers. counting numbers, natural numbers. Okay? That means if I will only take, my a sub n will be the general term. I can kind of call f of n, okay? I can't really put f of x, because as soon as I put x, we're really thinking about the x could be any number. That means I can really think about domain being all of the real numbers. But this one, it's not. Domain is only a positive integers. 1, 2, 3, 4, and so on. Okay? That means I can have 1, 2, 3, 4, 5, 6, and so on. That means only this. Okay. And then, I don't know, maybe this will be a sub 1. Maybe this one will be a sub 2 value, because we will have a values which corresponds to the, a sub 3. Yes, if I'm going a sub 4 and so on. That we can see, we can create a function. Okay, I mean, not really function, it's like just the points, but kind of it's like a function with the domain of being positive integers. Okay. Now, each sequence can have formula. It's like a function. Function like f of x has the formula. I don't know, x cubed, x squared, square root of x. The same for sequence. That means sequence, a sub n, could have the formula. And we can define formula inside this curly brackets. This one has more details, because this means that we really indicating that n will change from 1 to infinity. Okay, we know, even if it's not written, we definitely changing the terms from 1 to infinity. Okay, if we have this notation, if we really want to write down, sometimes you will probably see this. Okay, like from 0 to infinity. That means this is a little bit different, as I said, if we would like to start with 0. But please remember, 0 is the only exception. We can't start with negative numbers. Okay, no, we can't. Just 0. Yeah? Or sometimes we can even start, like, let's say we would like to skip a few first terms. We would like to start from n4. Okay, because you will see, because sometimes we don't want to deal with the beginning of the first terms, because they don't really match to our pattern. But then after, like, the term 4, we like the pattern, and we like everything match to our, like, solution. Okay, yeah, that's we will go the formula for the nth term, and I have a few examples. Okay. That means again the sequence. We may have, this is actually almost the same thing. We can use the formula, which is like preceding notation, is just the formula, or we can simply write out all of the terms. Okay, that's me. For example, I have example, but I can show you a sub n actually could be defined. Of course, most likely the formula is in terms of n, and we know what n means. That means, let's say 1 over n. Okay, that's the formula. Yeah, that we can see. This is just the notation, the formula. And can you tell me what is the first term of this sequence? If the sequence has the formula 1 over n. What is the first term? Oh, just 1. What is the second term? 1/2, of course. And what is the third term? It's just 1/3, and so on. Yes, 1/4, 1/5. Okay, that means that's what we can. That's, and we will just use, yes, or we can, yes, actually I like this. We can say, you know, I will switch the camera because I'm like writing on the screen, and it's weird. I'm like getting closer to the camera. And one thing is, do you remember sometimes I have like kind of delay, and I think it's because of the camera. That means I will switch off the video, but I'm still there. I will switch on at the end. And then we can see the whole screen. Okay, that means, yes, I really like this, because I will write 1 over n. And who can tell me, how can I define the next term after 1 over n? No, not 0. Oh yes, I mean, hang on. Too fast. Yes, of course, 1 over n plus 1, and eventually 1 over n plus 2, and so on. And one more question. How can I define one term in front of 1 over n? Yes, 1 over n minus 1. Okay, we can see, that's mean we understand this n plus 1, n minus 1. Good. This one we can close it. Okay. Oh, hang on, too fast. Okay, that's me now. What I have a table with a few formulas. Yeah, I gave you this one. It's nice. And let's actually, because probably I'm trying to squeeze everything in one slide, but since we're talking about this, because what I will show you later, which actually I mentioned about this, if we would like to see or define a sequence as a function, we can draw this outputs on the number line. Okay, that means this will be my formula, a sub n, and this is n. That means 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay? That means the first, for 1, we did have 1. For 2, we have 1/2. Okay? For 3, we had 1/3. 1/4, 1/5, 1/6. That means, can you see what's happened with this? Oh, I see some message. I can't hear any noise. Kyrie, can you hear a noise? Okay, I'm just testing. Okay. That's, we can see that's nice actually output, all of the dots. Not, you will probably see me sometimes like connecting this. Okay, it's nice. 4, 5, 6, 7, 8, 9. Because we will, one of the things we have to investigate how this sequence behaves if n is like infinity. That means as n goes to the infinity, what do you think? What 1 of n is doing? I will remove that arrow. Okay? That means if the n is infinity, it's 0. Yes, that means this goes to 0. It's like 1 over infinity. And of course, we will use, this is like weird notation, right? Like we really have a better notation. Limit, which is a behavior of 1 over n, as n goes to the infinity, is a 0. It's almost the same like 1 over x. Can you see the yellow line? Of course, we don't have, this is yellow line, like kind of represents a corresponding function. We don't have the values between, only the red dots represent the terms of the sequence. Okay, but kind of showing you the whole pattern, I will write this line. But we can see the yellow line is definitely approaching 0. Okay, that means this is the big thing, to find a limit of the sequence, okay, for this section. Okay, but let's actually reach that. Okay, a few formulas for the sequence. We may have n over n plus 1, or we can write like that. We can see the notation or the formula is almost the same. You can write like a sub n equals to the formula, or we can write just in the curly brackets. That's the same thing. Or we can simply write out all of the terms, expand it. 1/2, 2/3, 3/4, 4/5, and so on. Can you tell me how this sequence behaves? What will be the limit at infinity? 3/4, 4/5, 5/6, 6/7. What do you think? Having this formula, n over n plus 1. How this, okay, if it's 1, yes, that means this will go. We can see the terms are getting bigger and bigger and bigger, but never greater than 1. Yes, really good. Okay, that means it's kind of like calculus 1, just computing the limits. Right? Or if the limits are too complicated, we can think calculus 2, the indeterminate forms. Okay, we may have, okay, something like that, the same thing. Yeah? doesn't matter, this or this, but let's look at the formula, because now it's something new. It's -1 to the power of n. That means this is part of the formula, and then it's n plus 1 over 3 to the n. That means what this -1 to the n is telling me. It's really telling me, okay, let me ask you this way. What is -1 to the 1? -1. What is -1 to the power of 2? It's +1. Yes, I'm just reading the answers from the chat box. And again, -1 to the power of 3, -1. Yes, that's when yes, exactly. If you see this -1 to the n, this means that yes, all of the terms alternate. Okay, we do have an alternating at the moment is sequence. Next week we will talk about alternating series. Okay, that means we can see negative, positive, and so on. That means this -1 to the n, it's a little bit different than the normal function, but that's how the terms of the sequence are defined. Right? That means please note this one. I can't really ask you for this limit, because this -1 to the n will probably confuse you, okay? But we will still, as n goes to the infinity, how this sequence behaves. But let's don't answer. You will answer probably in half an hour, because I don't wanna confuse you with this. Okay, now I have another example. Okay, just square root of n minus 3. And the same, you can see I can use this notation, or I can use this notation. And for this one, you can see what is the difference. I did indicate the first, the value of n for which the first term will be defined. That means I would like to start with 3. Actually, I don't know if I would like to. I think I have to, right? Because based on the formula, I can't really have negative numbers under the square root. That means 3 must be the first number. 3 minus 3, 0, and so on. 0, square root of 1, square root of 2, square root of 3, and so on. Okay, that we can see. That's how, for this one, we really have to indicate this way. Okay, if we're using just the formula. This one is nice because we may put the beginning and end using the brackets and the index. Okay, and I have one more. Okay, trigonometric one. That means you can probably see we may have any formula, any formulas. It's like for the function. We can have just the polynomial, we can have logarithmic, exponential, trigonometric, root function, like we can have any function. We do have some answer. Would the third go to the infinity? Yes, the third one, of course. This one, it's expanding. Square root of 2, square root of 3, square root of 4, 5, 6, 7, 8, of course, goes to the infinity, right? Yes. The positive. Oh, no, it's just positive. Or would it be positive or negative? No, it's just the square root of 3, square root of 4, square root of 5, square root of 6, 7, 8, square root of big number. That means it's the big number, it's infinity. Because, right, we can't have negative numbers because it's square root, it's positive number. Yeah, that's me, no negative. Okay, and let's see this one. The formula is cosine n pi over 6. And now actually, I was gonna say, you can see for this one, I want to start with 0. That's what I said. Sometimes it's 0, sometimes it's different number. Okay, normally if it's not written, it's obvious that it's 1. Okay. And yes, square root, cosine of 0 is 1, and then cosine of pi over 6, square root of 3 over 2, cosine of pi over 3, 1/2, and so on. Okay, that's we have the terms. Okay, that means you know how to define a sequence using the formulas or the terms of the sequence. Okay, let's keep moving. Yes. Cosine can't have negatives. Oh no, cosine could be negative. Oh, hang on, too many questions. Let me clarify it. Positive, negative. Square root of 4 is positive. No. If we have, okay, first of all, if we have square root of 4, what is square root of 4? Who can tell me? It's just 2. Oh, I'm writing. It's just 2. Okay, thank you. That means it's just here. Now, if I have equation like that, x squared equals to 4. Okay, that means what is the solution of this equation? What's the solution of this equation? X squared, it's now, of course, now I can have positive and negative square root of 4, positive and negative 2. But we can see that's different. Okay, for this one, I didn't even have an equation I can remove. I only have positive square root of 4. I'm not like, I don't know, taking a square root of both sides. I don't even have both sides. It's just a number, and it's just 2. Okay, yes, that's what it's, no, it's, it's not embarrassing. It's actually, we do have this confusion sometimes. That means square root of 4 is just 2, but x squared equals to 4, that's different. Okay, that we clarify this. Okay, what about the next question? Cosine can't have negative. No, cosine could be negative. So negative infinity. No. This one also no. We will leave this one for now. Okay, because cosine, we know how cosine behaves. Oh, that's sine actually. Cosine is like that. That means a few numbers are positive, 0, and then a few numbers are negative, 0, positive. That means just, I don't know exactly where will be the dots, but we can see, of course, only the dots are the output of the sequence, but could be positive, negative, positive, negative. That means this limit most likely will be undefined because cosine like oscillate between 1 and negative 1, 1 and negative 1. Okay, oscillation, right? That's, we also have, no, we also have, let's put question mark. Yeah, I can actually say the limit is undefined, but we will come back to this because I can't say, it's kind of like plus or minus 1. I can't put 2 numbers. Now, okay, no more question, good. Okay, that's me. Now what we have, I have a few exercises. And what I would like to do, I would like to find with you a general formula for A sub n looking at the expanded form. That's what I have. I have a numbers -1, +1, -1, +1, -1, and so on. That's what do you think, assuming that this pattern will last for for the infinitely many terms? Okay, that's what do you think? How can I find one formula to define this? It's kind of the other way. Instead of having a formula and expanded, we're looking at the expanded form and we have to make a compact formula. Do you know how this values behaves? What will be the formula? -1 to the, yes, thank you, -1 to the power of n. -1 to the power of 1, negative. -1 to the power of even numbers, positive, and so on. Yes, really good. We can also say, we can play sometimes n plus 2, am I right? Hang on. Because the difference is if I will start with the positive numbers. I also want you to know this. That means when I'm starting with the positive numbers, I have to say n plus 1. Okay, because 1 plus 1 is 2. That means I will get even number for the first one. And then so on. N plus 2, what n plus 2 will give me? 1 plus 2 is 3. -1 to the power of odd number is negative. That means this is actually equivalent. Okay, and n plus 2, n plus 4, we still have an odd number as a first number, okay, if n is 1. Okay, but this is, of course, that's the most common. But if the first term is positive, we have to put n plus 1. Or n minus 1, because then it's 0. It's still fine. Yeah, that means, please note that this is equivalent. Okay, exercise number 2. Find the formula for the general term a sub n of this sequence: 2, 4, 6, 8, 10, 12, 14, 16, and so on. That's what do you think? How can I define these numbers is just, of course, 2 times n. Thank you, really good. That's sometimes it's challenge. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and so on. That means 2n will represent an even numbers. Even numbers. Okay, and now, probably you're not surprised, exercise number 3. How can we define odd numbers? 1, 3, 5, 7, 9, 11, 13, and so on. Thank you. Really good. Because we can take even number, and actually we can subtract 1, okay? Or sometimes, but this is different, we can add 1, but then I have to say that we're starting from 0. Make sense? You can see that's equivalent, because when I start, that's my n, not h. When I start with 0, 2 times 0 is 0 plus 1, it's still 1. It's still giving me my, that means 2 minus n is the most like frequent, because we always start with 1, but at some reason, if I would like to start with 0, that will be the case. Actually, can you tell me the formula if I would like to start with maybe 5? How can I figure out? Yeah, I will start with 2n, but I still want my first term to be 1. Oh no, minus 4. Let's try. 2 times 5 is 10. 10 minus 4 is not 1. Minus 9, yes. Okay, just in case if we have to like play with this. But of course, this is just the exercise. The most frequent is this one, and occasionally this one. Okay, good. What else I have? Oh, now I kind of pick, not random numbers, but yeah, let's see. Okay, how these numbers behaves. First of all, what I see positive number, negative number, positive number, negative number, positive number, and so on. That means what will be one part, yeah, we do have squared numbers, but one of the things, I have this. I have negative 1 to the n. Actually, n plus 1, because the first term is positive, if I'm starting with 1. Okay, now I have numerator and denominator. Let me indicate we're really starting with 1. Okay, how denominator behaves? 5, 25, 125. It's just 5 to the n. Really good. 5 to the power of 1, 5 to the power of 2, and so on. And what about numerator? 3, 4, 5, 6, 7, and so on. But we starting with 3. That means how can what formula I will put here? Yes, n, just n plus 1, n plus, hang on. Oh, I have n plus 2, I think. Yes, it's 1 plus 2 is 3, 2 plus 2 is 4, and so on. Okay? Okay, that's, we can see it's nice, yeah? Nice way to like look at the patterns. Yeah, it's like the IQ tests. That's what they always ask us. Okay. We practice this. What else? Oh, I did type my solution in the corner. Oh, can you see what I did? I put n minus 1. I think it's still correct, because 1 minus 1 is 0, negative 1 to the 0 is still positive 1. Okay, plus 1 and minus 1, both of them are good. Okay, let's see what else we have. Oh, okay. That means so far we did have the formulas for a sub n, which the whole formula depends on n. Okay, that we had like, yes, we had 1 over n. I mean, one of the formula was, actually I can I come back for, okay, like let's see this one. N over n plus 1, n plus 1 to the power of 3 to the n, negative 1 to the n minus 3, cosine n pi over 6. That means all of the formulas depends on n. Yeah? And it's easy to deal with this 2 to the n, 2n minus 1, 2n plus 1, and this one. What we also have, we have a formula for the sequence, which is not really defined like explicitly, like in terms of n. it's the formula that is defined in terms of the other terms of the sequence. Okay, I know it sounds probably complicated, but it's not. And then we call that sequence is defined recursively. That means the sequence is defined, it's like implicitly, not directly in terms of n. That means the main formula, let's say on this side, actually one of the most famous sequence which is defined recursively is the Fibonacci sequence. I hope you heard about these numbers, okay? The magic numbers, the golden proportion, the golden numbers, okay? That means this is the definition. And just because this is the Fibonacci sequence, instead of a letter A, we're just using F. But that's the same. That means you can see F sub n, or we can even say A sub n. F sub n is defined as a sum, yes, addition of two terms, okay? F sub n minus 1 and F sub n minus 2, okay? And we're starting from 3. But also, what is important, if we do have a recursive definition, we always have to have additional information. That means they providing for us term 1 and term 2. It's 1, 1. Oh, I have the numbers, but I wanted you to give me the numbers. That means the first term, it's 1. The second term is 1. I'm just copying from here, 1 and 1. And now we will create the third one, okay? And one more time. The third one, which is the nth one, the third one, if n is 3, I will have f sub 3, is defined as an addition of two terms which are before the actual one. That means f sub 3 will be defined as a f n minus 1 will be 3 minus 1, and n minus 2 will be 3 minus 2. That means I have to add two terms which are before my next one. Okay, that means can you tell me what is the f sub 3? What is the third term? It's simply 2. Now, how can I define the fourth term? I have to add the third one and the second one. Two terms in front of the fourth one. Okay, what will be the next term? Who can? 3, thank you. Can you tell me the next one after 3? 5, yes, we're just adding, yes, we're just adding this one. After 5, 8, okay, after 8, 13, and maybe 2 more after 13. Oh, no, 21, thank you. And after 21, just one more. Oh no, after 21, yes, okay, you're right, 34. For some reason I thought, okay, that we can see, looks like, and I did type, okay, I typed until 21. That means this is, yeah, this is the way, yeah, this is the way to define the numbers. I mean, having a little bit different, yes, different form of defining. And it's not helpful most of the times because you can see, like, do you think you can tell me, like, what is F, like the 99th one? Of course we don't know. We really have to add. We have to follow the formula. That means it's not easy. It's not easy to get this one. But if I have the formula, like the normal formula, let's stick to this one, 1 over n. Can you tell me the 99th one? Yeah, what will be the formula? What will be the term? Of course, yeah, of course. As simple as that. We can see we can definitely take the advantage if we have the normal definition. But if we have recursive definition, we can still get the 99th one, but we need time. Okay, that means that's the thing. Okay, that's me. Now let me just maybe spend 2-3 minutes about talking about these numbers. Probably you think that they are like kind of random numbers, but believe me, they are not really random numbers. We have lots of connection and we have lots of patterns, lots of like behavior in the nature that actually corresponds to these numbers. Okay, like 1, 1, 2, 3, 5, 8, 13, 21, and I can show you some of them. Let's look at my first example. Oh, this is my nice drawing. Okay, the golden proportion. If you will look at the tree, I know, sounds funny maybe, but maybe not now, because I'm assuming that everybody has a dark, no sunlight behind the window, but maybe tomorrow, when you look at the tree, the normal trees, because some of them are like mutated, the normal trees, they should actually grow like that. We have like kind of like the first branch, and then looking at the like second level, we will have only 2 of them, and then only 1 of them will expand, and we will have 3 of the branches, 5, 8, 13, and so on. That's I know sounds weird, but that's how the trees grow. Okay, let's look at another. Oh, that's scary. Also in our like bone, the whole length of the bones and the whole body, it's also related to these numbers. That means this has like 2 units, this will be 3 units, this will be 5 units, 8, and so on. And of course we have to go to the whole hand, and okay, that's another nice. And you can, I don't know if we can, but we can try to measure. Okay, let's look at my, oh yeah, this one is a little bit different. This one is just like, because this number is also weird. 1.6, that's the golden proportion. 1.6 or 1.7. Yeah, we do have some, but I can show you 1 second, because this is also related to these numbers. But for this one, I have like, what you can try to do, you can try to take a pencil and a paper and try to draw a rectangle. Okay, like everybody will try to draw a rectangle. Maybe not now, maybe you can do later, but try to draw a random rectangle. And what you can do, you can measure the width and the length and get the calculator, okay, measure the width, measure the length, and get the calculator and get the ratio, length over width. Everybody will get something to similar to 1.7. Doesn't really matter who will draw the rectangle. Okay, that's another thing, but let's hang on. Okay, because now we can actually see this is kind of this rectangle. Okay, that's when you, and also in this rectangle, if I will kind of like divide this, having a rectangle, I will make like a square, and then again in this part I will make a square, in this one I will make a square, and again the 8 will give me the square and the square and the square. That's and all of these areas will be like, that's the numbers. Okay, if the ratio, of course, if the ratio length over width is 1.7, which always it is, that you can also see the areas. Okay, will be like, of course we can think about the percentage, but this will be the numbers. Okay, and I have, okay, my another drawing. I don't know if you know Pascal's triangle. Yeah, like look at the dark numbers, 1, 1, 1, 1, and we always adding. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is also 3, and we always starting the lines with 1. But if I will take kind of like a diagonal lines, this is 1, this is 1. Now this line, 1 plus 1 is 2. 1 plus 2, and this will be another 1. Oh, no. 1 plus 2 is 3. This one, oh no, this one is still full line. 1 plus 3 plus 1 is 5. 3 plus 4, and I think this will be 1 over there. Okay, it's 8. And 1 plus 6 plus 5, and I will have another numbers. 1, it's 13. That's when you can see the pink numbers. Yeah, but just Pascal triangle, we know how to get this, but look at these numbers. They are the Fibonacci numbers. Right? That's we have lots of different ways that we will actually see these numbers. Yeah, yes, yeah, it's really, yeah, that's the numbers. They are almost everywhere, I can tell you. Yes, it is cool. That's I always, of course, I love mathematics, and I want everybody to learn this subject, but we kind of connected through the numbers. Okay, do I have something else? No, I don't have it. Okay, but you can, yeah, you can definitely try maybe to Google a little bit more about this golden proportion. Yeah, it's nice. Yeah, yes, yeah, it's fine, nice stuff. The numbers. That's mean maybe you will switch your major and maybe you will study mathematics and especially the number theory. Yeah, that's what the mathematicians do. They're really looking at some patterns but yes, but this guy Fibonacci, yeah, quite yeah, interesting. Okay, let's come back to our calculation. That's in what I have. I do have a formula. It's just the random formula, but we can see is the recursive definition, recursive formula. That means what? Oh, my little bit. This is the formula. And I just want to check if we really understand. Okay, that means, oh, I don't have the solution. I will write with you. I want you to use this formula, the recursive formula for the sequence, and let's just try to list 4 terms. Okay, that's we do have the first one, 3. Now, let's see how the second one we can compute. The formula is defined as a sub n plus 1. That means always n plus 1, always the next one, which 2 is 1 plus 1. It's defined as a half of a sub n plus 2. That means a sub 2 will be defined as a half, and this is telling me that it's 1 less than n plus 2. That means this will be 1 plus 2. Okay, that means I only have to substitute the one term before, which will be 3 plus, I can write it down. No, of course I'm writing the final answer, 5 over 2. Yeah, okay, that's me. Now your turn. Who can tell me? This will be 1/2, and what shall I type? What shall I write here? If this is a sub 3, this will be you calculating. Oh, you can tell me the formula. I can put a sub 2 plus 2. Okay. Oh, you have the final answer. Let's see. You do it with the fraction. That means this will be 1/2, 5 halves plus 4 halves. That means it's 9 over 4. You're right. Really good. And 5 halves. Oh, yes, you did put 5 halves. Okay. For some, I was like waiting for a sub to answer. Okay. And the last one. Oh, who can get the answer first? I will write a sub 3 plus 2. That's when we can see. We really need the term before. Okay. 1/2, 9 over 4 plus 2, which is 8 over 4. Oh, is that correct? It is 17, but what is in the denominator? It's, yes, 4 times 2, 8, because we did have half in front. Okay, that's what we can see. You can definitely compute the term by term. It's not helpful, as I said, because if I will suddenly need like a 99th or 100th term, I really need to spend time and add all of these together. Okay, but that's the recursive definition. Okay, let's keep moving. Okay, that's me now. Sequence, what I want. Let's see, you just know this. Okay, that's what I said on my like few slides before. Having a sequence, and I pick this one. I can even put this. Oh, actually I don't have to because I have a sub n. Okay, having a sequence n over n plus 1. That's all of the terms expanded. 3 dots are missing. And we will probably use for the plotting, for like the geometrical like explanation, we will use the XY plane. That's what I did. I didn't mention about the number line, but we can also do on the number line, but this will be just the numbers. We're not indicating like 1, 2, 3, 4. That we can see the first term is 1/2, and then the second term is 2 over 3, 3 over 4, 4 over 5, and so on. Okay, and of course we can see that's the limit. But this is like 1D is a little bit too less. We'll at least 2D. That means one term is, the first term is 1/2. That's the second term, the third one, the fourth one, and so on. Oh, we do have nice 7 on the graph. Okay? That we can see, yeah, that the dots are getting higher and higher and higher, but never higher than 1. And I think you told me the limit. The limit will be 1. Okay? That means that's how we will plot the points. Okay? We will use a number line. The XY plane, Cartesian plane. Okay? We know that. Oh, and now, important, I mean, you probably know this. That means that's what we will do as soon as we can plot the points, okay? We can compute, I mean, we can investigate the behavior of the sequence, the terms of the sequence. That means we will look at the limit of the sequence, and let's say the limit of the sequence is L, or as I also use this notation on the previous slides, but this is not, that's the better one. Okay, that's mean looking at the limit of the sequence, we're looking how the terms behaves at infinity. And now we may have a situation that the limit exists, okay, and if the limit of the sequence exists, we will call that the sequence is convergent. You probably learned this terminology in section 7.8 for the improper integrals, right? Like if the integral was defined, we will call convergent to. If the integral was not defined, or we couldn't find like the answer was divergent. Okay? That means the same, we will adopt the same names for the sequence. That means if the limit exists, we call the limit, the terms converges to, I can say to 1. Limit of n over n plus 1 is 1. That means we can say this sequence converges to 1. Okay? I can actually converges to 1. That's what we have to do. Okay, or we can simply say convergent. Or if the limit doesn't exist, we can say divergent. Or hang on, if doesn't exist, or if it's infinity. Okay, that means if actually the terms, like let's take something simple, 2 to the power of n. What do you think, how these terms behave? Oh, that's actually really... Okay, what is the first term? Who can tell me the first term? 2 to the power of n. Yes, let me write. A sub n is defined as a 2 to the power of n. It's 2. What's the second term? 4. The next one. 8. One more. 16, right? And yes, and so on. That's what we can see. We will have 2, we will have 4, 8, 16, and we even know how the... I can also start maybe with 0, 1, 2, 4, 8, 16. If I will say that I like n to be 0, okay, as a starting point, then we will have 1. But that's not really. And we can see this is nice exponential function. Of course, we're looking just at the dots. That means this, and what will be the limit? Limit of 2 to the n as n goes to the infinity? Of course, infinity, but we will say divergent. Okay, it's simply divergent means like it's expanding without the bounds. Yes, thank you for the answer. Okay, few more things and I will finish. Okay, that's what we have now. Yes, you learn a lot today. I'm so happy. Okay, this is just a graph of showing how we can see the dots, which are the terms of the sequence, can behave. That's what I was saying. Like, let's start 1, 2, 3, 4, 5, 6, 7. Okay? That means I really like to start from 7, and now we can nicely see the limit. Even having a few terms before is still fine, but kind of like from 7 is we are consistent. The terms are getting smaller and smaller and smaller, but never less than L. Okay, even with this, we're still looking at the limit at infinity. That means for this one, limit is definitely L, even starting with 1. But if we would like to make other things like right, I would like say, okay, let's just look at, start this term, I mean this sequence with the term 7. Okay? But it's still fine for this limit to start with 1. Or we may also have this nice behavior. This is probably -1 involved. We can see it's like, kind of like the terms are oscillating. They are getting closer and closer, okay, and eventually to that line. We may also have this, and we can also say the limit is L also. Okay, that means even for this one, the limit is L. What is change? Oh, no. I just said, okay, no. We can take all of the terms. We can really take all of the terms for the limit. I don't want to confuse you. The only thing is, we may have a situation that we really like to see the same pattern, because we can see what's happened. From 1 to 7, the terms are actually increasing. And then suddenly they have a nice, beautiful pattern. They approaching L. No, we don't. That's what you're probably asking. How many points should we plot before we can? No. It's you will see, because we will. This is just an example. We will have a formula. You will see all of the terms, and you will. And it's too soon to talk about this. For now, it's definitely the behavior at infinity is L. Even if we have a little bit weird situation for the first finite numbers, doesn't matter. But now you will see we don't really have to cut this. It's even starting from 1, the limit is still L. Makes sense, I hope. Okay, no, we don't really have, that's I think what you're asking. How many points should we plot before we can declare? Oh, hang on. What you asking? Am I crazy? You just asking for the, like, how many points we have to? No, probably we will not even plot the points. We will simply use the formula. Okay, let's look at this one. Can you see what I did? I plot like 0, 2, 4, 8, and it's obvious. And it's obvious that the terms are going to infinity. Yeah, that's me. No. We will probably not even plot the points, or occasionally when I ask you, or we will not even miss the terms. Based on the formula, you will know 2 to the power of n. Of course, 2 to the power of big number is a big number, infinity. That means you will know this limit without even plotting. Yeah? Okay. Okay, plotting 6 points and not see that the pattern goes back down. Oh, okay. Okay. That's, yeah, I see what you're saying, because you will plot this, and this, and then you will say, oh, function goes, I mean, the terms going up, infinity. Okay, I see. No, yes, that's what, okay, because you don't, that's what I said, we don't know if the function goes possibly like that, yeah? That's me, no. You will definitely know based on the given formula. Okay, no, I will not confuse you that, oh, the first like 100 terms goes like that and then suddenly are going down. No. You will really know that. Okay, let's actually see, because I do have a few examples. That's me, don't worry, no. Because I can't ask you to plot like the points and trick you. Yes, no. Okay, yeah, that's another example. Actually, you can see what this actually is. This is talking about the corresponding function. That means when we talk about the sequence a sub n, I can theoretically think that this is my function, but we can see only the dots are important. That's what I'm doing with the yellow line. Yes, I'm kind of like thinking about the whole function, but I'm only looking at my dots, my terms of the sequence along the line. And then we can change this function even like have f of x and compute a limit. But this limit will be, of course, limit for the sequence. Okay, that's me. Again, it's a similar situation. It's like we don't know how many terms, and then suddenly it's the nice limit. But no, don't worry for this. The limit, of course, is L. This is just, yes, indicating, this theorem is indicating that A sub n could be equivalent to f of n, or even f of x, just the normal function. But we're still thinking just about the dots. Okay, and now, yeah, if the limit is infinity, we're just saying divergent. Okay, we don't really have to. I just type all of this description, but we don't have to. We're just saying it's divergent. Divergent means like it's expanding without any limits, without the bounds. Okay. And now, computing a limit for this of the sequence, we will simply like adopt all of the limits law from the chapter, I think was chapter 1. From chapter 1 from calculus 1. That means the limit of the sum is just the sum of the limits, the limit of the difference of two limits, limit of the constant and the function, we can put constant outside, limit of the constant is just the constant. Like we can use any property for the function we can adopt and we can use for the sequences. Another one, limit of the product of two limits, limit of the quotient, of course remembering 0, power function, I can compute the limit inside and then take the power, any property. We also had a squeeze theorem. You remember, like if we can squeeze our given sequence between two sequences, right, like L sub n and C sub n, then I can compute the limit of B sub n. If, of course, let me write different. If this limit is L and this limit is L, then the middle one is also L. Okay? That means that's another squeeze, another property from the limit. And then, okay. This one is also a property, a tool to compute a limit, but this one is different. We didn't use this for the function. That means this one you can maybe like really highlight this and take the notes. This one is telling me what? It's telling me this. If the limit at infinity, of course, always at infinity, because we're looking at the behavior at infinity, limit of the absolute value of the original sequence is 0, then the limit of the original sequence is 0. Okay, that's what we can see. We may have this limit of A sub n, and we may not know what to do with this, and then you can think, oh, if I will take the absolute value, then the formula simplifies a little bit, and then I know what to do. That means you may try to take absolute value of the original formula and get the answer. If the answer is 0, then the original sequence is also 0. But please remember, this only works for 0. If the absolute value, let's say, is 1, then this is not 1. If the absolute value is, I don't know, 10, this is not 10. Okay, then we can't use this. This is like a tool, it's like a property. Only 0 works. Okay, only 0. Okay, and then I have, that means what we will do, I still have a few new things. Wow, the section is quite long, but I don't want to keep the section. I will probably have a small video for you just covering a few things that I miss. But what I would like still to do, I would like to solve a few limits of the sequence for few important functions. That's me. Let's see, exercise number 1. What is the limit of this sequence, n over n plus 1, which you probably know the answer because we did this today, right? Okay, that means this is simply 1. You can think, if you like, we will not do this very often, but you can even think about this function, yeah, like corresponding function. That means this is definitely 1. And we also remember limits at infinity. If we have a ratio of two polynomials, we're looking at the degree. If the degree of the polynomial is the same, we're just taking a ratio of the leading coefficient, 1. If the degree is greater on the top, it's infinity. If the degree is greater in the denominator, then it's 0. Okay? Okay, but we have 1. Oh, and we even recognize the graph. Okay, another exercise. Oh, okay, we can actually have this. Okay, now limit of the sequence natural log of n over n at infinity. That means hopefully you remember something from yesterday, but I can show you a few things. Okay, that's mean what we have. Do you remember the indeterminate form? Natural log at infinity, of course, is infinity, and infinity is infinity. That's we actually have infinity over infinity. Okay, and yes, Kevin, yeah, I know. We can also get the answer right away, which I will show you the shortcut. But I also want to use the rule that you learned yesterday. Okay, that's mean infinity over infinity. We know that is one of the 7th of indeterminate forms, and having that form, we can use the L'Hopital rule right away. Okay. The only thing is with the L'Hopital rule, some of the mathematicians, I can say most of them, they really have a problem using a L'Hopital rule like right away with the n notation. That means as soon as you will decide to use the L'Hopital rule, the mathematician, they want you to define, just to rewrite this in terms of x. Because what's happened, the L'Hopital rule is telling me that I have to take the derivative, right? I will write h. I don't know if Dr. Bank was writing h. I'm always indicating this, that I'm using the L'Hopital rule. Let's actually do it. Do you remember the L'Hopital rule? We have to take the derivative. What's the derivative of ln of x? 1 over x, thank you. And what's the derivative of x? 1, because we're taking the derivative of the numerator and denominator separately. And now 1 over big number is 0, of course. That means this is the same answer. But because we did the derivative, and we know that we can't differentiate if the function is discontinuous. Having n, looking at everybody will see, all of the mathematicians, when they see n, they will think about these dots. Yeah, they will only think about dots, I don't know how the terms looks like, but they will think the dots. And I can't just differentiate just the dots, right? We don't have derivative. But if we will think about x, then we're thinking about the entire, my curve we will think about the entire curve. Okay? That's the reason that when we're using the L'Hopital rule, always please rewrite the sequence in terms of x. Of course, I'm not testing, I'm not checking your writing, but just please to remember. Okay, but another thing, what we can do, since we're computing limits at infinity, and we have the ratio, yes, ln of n over n, we can try, I can get some space. Because the thing is, and it's actually really important, I also don't know if the Dr. Bank talked about relative growing rates, which function grows faster. Did he talk about this? Okay, he did. Okay, good. That means we know based on this, because then it's a really nice shortcut if we understand this. That means let me write maybe something like that. X squared plus 1 over x plus 5. What do you think? What is this limit at infinity? It's infinity, because x squared, numerator is winning infinity. Great. What about this limit? Limit at infinity of x plus 1 over x squared plus 2. Yes, denominator is winning, then it's always 0. And of course, you probably guessing 2x minus 1, 3x plus 5. What is this limit? Oh no, it's not 0. No, its degree is the same. Then we're taking the ratio of the leading coefficients. Yes. Okay, that means based on this, what we can see nice pattern. If the function on the numerator is growing faster, because x squared is definitely growing faster than x, has bigger values, x squared, like squaring the values are higher than just the value. Okay, that means if the numerator grows faster, always the limit will be infinity if we have the ratio. If the denominator is growing faster, then always 0. If they have the same degree, this means that we can compare them, and the limit is the ratio of the leading coefficients, 2/3. Okay? It's kind of like same speed. Yeah, yes, actually this will be the same, because doesn't matter if the function is 2x or 3x. I know that the slope of 3x is a little bit higher, but really at infinity doesn't matter. Doesn't really matter if I have 2 times big number or 3 times big number. Okay? If they completely change the degree, like x squared, x cubed, that's different, but they are almost the same. For the really huge numbers, it doesn't matter if we have like, yes, the line. I know that you can probably logically think that's 2x, or maybe let's say 3x, and that's 2x. That means the slope 3x, 2x. That means 3x is a little bit higher, but doesn't matter. I can tell you at infinity they will be almost the same. Okay, that means always when it's the same degree, they are comparable, and it's the finite number. Okay, and now looking at function ln and n. Okay, do you know which function grows faster? Which function has higher value at infinity? Of course, the denominator, right? I can maybe draw, this will be ln of x, and this will be x ln of x. Of course, we're still talking about the sequence. That means I'm talking about the dots, but doesn't matter, the pattern is the same. Okay, that we can see x, which is n, it's winning. Let me put actually n. I just like to use ln of n. That means since n is a faster function than ln of n, we know the answer right away. Okay, that means we could put 0 even without this L'Hopital rule. Okay, that means we have to know which function grows faster. You can always look at the graphs and then assume the limit. Okay, please use these rates. Okay, exercise number 3. Determine whether the sequence -1 to the n is convergent or divergent. What do you think? Does this then is divergent, because it's not really going to the infinity, but it's like oscillating. Okay, that means it's definitely divergent. The limit doesn't exist. -1, +1, -1, +1. That means it's like jumping from one value to another. Limit of this is simply undefined. And this is the conclusion. Okay, good. Okay, let's keep moving. What about this one? Limit at infinity of -1 to the n over n. It's 0. It's 0. We can think. Did I draw? No, I didn't draw anything. I can think -1 to the n. It's not a proper function, but I can think that these values behaves like that. Just +1, -1, positive, -1. But my denominator is huge, it's infinity. That means 1 over infinity or -1 over infinity, of course, give me 0. Okay, it's just simply this, but this is really informal. Now, I really would like to show you what will be the formal way. Now we can use our new tool and we can take the absolute value. That means I can take my original sequence and I will take an absolute value and I will test the absolute value. Absolute value of n is just n. Absolute value of -1 and +1, it's always 1. And now 1 over n and infinity, of course, is 0. That means this is really informal, but if the absolute value is 0, then the original sequence also has a limit 0. Yes, you remember only 0 works. Then I can make this conclusion. That means that's how we can, that's the moment that we can use. And even drawing these terms, they really alternate because has -1 to the n. Okay, let's find a few terms. -1 to the n over n. -1, +1/2. -1/3, +1/4, and so on. That's when we're starting with -1, +1/2, -1/3, +1/4. That means it's actually kind of like, I always call like a snake. Positive, negative, but the absolute value of this are getting smaller and smaller. Okay, that's we can see it's like alternating between positive and negative, but the terms are decreasing. Okay, that means it's definitely 0. Okay. What about this one? Determine whether the sequence converges or diverges. If it is convergent, converges, find the limit. Sine square of n over, would that last one be convergent? Oh, hang on. Yeah, yes, convergent to 0. Yes, I should actually convergent to 0. Of course, always when we're getting a finite number, even 0, it's convergent. Yes, thank you. Okay, that means this one, we have to find a limit. Yes, this one is convergent, but do you know the answer? Convergent to what number? We can also think like how function sine behaves. What's the maximum value? It's not really, no, it's not 1/3. We have to think in terms of infinity. That means 3, again, this is really informal. We can't write like that. But yes, it's 0. That means this is big number, right? 3 to the power of 1, 3 to the power of 2, 3, 4 is huge number. This one, oh, it's not even, the maximum number is just 1. Okay, that means this is really 1 over big number is a small number. But let me remove this, and we do have a nice property which we call squeeze theorem. Function sine has the values between -1 and 1. But when I square the values, the negative, the square, I mean, no negative values. All of the values will be positive, but squaring 1, I still have 1. And now, what I can do, I can create my formula. I will divide by 3 to the n. That's actually 0. 1 over big number is 0. That means if both of them are 0, the middle one is also 0. And that we can definitely use the squeeze property. Okay? Yes, okay, good. Yeah, 1/3, actually, it's also, I saw answers like that. It's funny. It's funny how we can, yeah? That's mean it's converges to 0. Okay, let's see if I have, oh yeah, that's another property. We can kind of evaluate the function inside and then outside. Don't worry, I can show you a function like this one. Find the limit of the function of the sequence sine of pi over n. That means what the previous slide was telling me, that I can compute, actually, I can compute a limit of the inner value and then apply the outer function. Okay, that means what will be the limit of pi over n? Pi over huge numbers, of course 0. And sine of 0 is 0. Converges to 0. Good. Okay, and now, oh, this one is interesting because we have n pi. N pi means 1 times pi, 2 times pi, 3 times pi. That means this one, let's actually find a few terms. It's not a common practice, but sometimes we can do this way. Okay, get ready and tell me all of these values. Maybe one more. Okay, do you know cosine at 1 pi? What's the value? It's, yeah, it's -1, okay. -1, -1, okay. What about cosine at 2 pi? 1. 3 pi, -1. 4 pi, +1, and so on. That means what actually we can see that cosine of n pi actually behaves exactly the same like -1 to the n. But we want, yes, if n is equals, we're starting with n1. Because then we have -1, +1. That means this, and I can tell you it's only function cosine and only n pi. The other functions we can't really get like some proportion and get also -1 and +1 and so on. That means only cosine n pi, it's equal to the -1 to the n. Okay, that means this one limit is really undefined. Now I can say divergent because it's oscillating between -1 and 1. Okay. Okay, what about this one? A sequence with the formula e to the power of 1 over n. It's just e to the power of 0, 1. Correct, thank you. E, and then I can focus on the inner function. 1 over infinity is 0, e to the 0 is 1. Convergent to 1, converges. Converges to 1. Excellent. Do I have something? Okay. Okay, I have 3. I don't know if you can stay with me. 1, 2, 3. Okay. Let's solve 3 of them and we will be done. Okay, this one. Can you tell me this limit? Limit at infinity of 4 to the power of 1 to plus 3n, and 1 over n, I mean, nth root is 1 over n. Yes, correct? And now I can distribute, because when I have one power and another power, I can distribute this. 3n over n is just 3. Okay? That's me. What do you think? What is the limit of this? Of course, we're focusing on the limit of the 1 over n plus 3, just the exponent, and we can apply. That means 4 to the power of what number? Yes, 3, which is 64. Nice, yeah, because this will be 1 over infinity, 0, 0 plus 3, 3. Okay, good. 64, right? 64. Okay, because that's bad to make arithmetic mistakes. Okay, and another one. Arctangent of, actually, let's just say n. I don't have to confuse you, at least today. Okay, that's me. What is the limit of, why did you need to do anything with the x? Why didn't you, hang on, I don't understand the question. Why didn't you need to do anything with the exponent of 1 over n? Oh, no. What is the, no, doesn't mean that I'm doing anything, just limit of 1 over n at infinity is 0. 1 over big number is 0. Yes, that's, no, I'm not really ignoring this. This is just 0 plus 3. Okay, oh no, I'm really taking this under the account. And then it's 3, of course, yes. Yeah. Okay, now, because we got the answer pi over 2 for this one, and I think it's correct. Arctangent of n at infinity, if you feel more comfortable, I can write this notation. That means how inverse tangent behaves at infinity. Of course, yes, I did have the answer. I can use my yellow and I can, oh, no, that's, hang on, how the function looks. And I don't even need the negative values. Okay, and we know the limits. It's pi over 2. We're not looking at the entire, we're looking at inverse tangent at 1, 2, 3, 4, 5, and at infinity is increasing, but never greater than pi over 2. Converges to pi over 2. Very good. Okay, and then I have one more. Actually, maybe do you remember that limit from yesterday? I mean, I hope, I didn't watch the entire session of Dr. Bank, but I hope, did he cover this function? What do you think? Or maybe it doesn't matter, I can still repeat this. That means this will be my last limit. Because what we have, okay, it's okay, okay. Because of course, probably yesterday's session was also extremely long. Because what we have, if I will write this as a limit at infinity, I do have 1 plus, let me rewrite as a x. X goes to the infinity, 1 plus x over x. Okay, that means what I have, 1 over infinity, 1 over big number is 0. That means I have 1 to the infinity. And do you remember, this is one of the indeterminate form. Okay, that means probably in order to find out what is this limit, we will use the L'Hopital rule. And that's the reason that I put x. Does somebody know what is this limit equal to? No, okay, no, we're not gonna guess. Okay, if he didn't cover, that means let's just do it, okay? But I can tell you, I really want you to remember this limit. Oh, he did this. That means, do you remember? Okay, do you remember the answer? I can simply repeat this. Okay, never mind, I don't want, yes, it's fine, it's okay, because that's what we will do. Yes, I will definitely repeat. Having the power indeterminate form, we have to really rewrite this. Okay, that means I will rewrite limit as x goes to the infinity, and I will rewrite the whole quantity as a e to the power of ln, and I will copy this quantity, because hopefully we know that e to the power of ln of a is just a. So like a cancellation equation, e and ln is gone. That means e and ln is gone, and I can focus on this. But I will keep this exponential form, because that's the only way that I can do it. That means I can keep my e function, and I can focus on the exponent. Limit at infinity. Having that x and ln, I can put this x in front. We also know that property. Okay, and now let me put, maybe I need this limit. Okay, I really have to find this limit, and the answer will be e to the power of a number. If the number is 0, the answer is 1, but if we will see, oh, 0, e to the 0, 1, no. Okay, now let's see. That means what I will do, I will copy only this limit. Actually, I can use the blue box. And let's find out. That means this is limit as x goes to the infinity, and I have x ln of this. We know that when we have a product, we have to change for the quotient. That means I will keep ln of 1 plus 1 over x, and that x, instead of multiplying by x, I will divide by 1 over x. And now let's check. 1 over infinity is 0. ln at 1 is 0. 1 over infinity is 0. That we do have 0 over 0. Okay? Yes, 0 over 0. And we're ready to use the L'Hopital rule, because this is another form that is letting me to use. Okay, let's try. Oh, not n, x. Okay, derivative of ln of 1 plus 1 over x will be 1 over this quantity times derivative of the inner function. Derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. In the denominator, I have just 1 over x. Derivative of 1 over x, negative 1 over x squared. Wrong. Negative 1 over x squared. I don't even need the parentheses. Okay. Now I can simplify this. And what's left? Limit as x goes to the infinity. I don't even have to simplify. I can compute this. 1 over big number is 0. That means we do have 1 plus 1. I mean 1 plus 0, 1. 1 over 1, 1. That means my blue box is 1. That means what is the final answer? The final answer is E. Yes. I can make more space. That means E is the final answer. That means please remember, I can update my box. E. I mean, I should put a limit actually. Okay. S. As n goes to the infinity, of course. This is E. As n goes to the infinity. That means this limit is equal to E at infinity. Also, yes, funny. E is like 2.7, and these numbers will give me E. Okay, that means please remember this limit. Okay, we really like, and yeah, it's just we really like this limit because it's quite important. Okay, yes, yeah. And as I said, I do have a few things, but probably it's like 10-15 minutes, and always is a little bit longer, I know. That means what I will do, you can watch for additional small, like short video. For now, I will finish the session. I think I covered the most important thing, which are the limits of the sequence. Okay? Thank you for tonight, and thank you for staying with me and answering all of my questions. Yes? It really counts. Thank you.